on the moduli space curvature and the weak gravity conjecture. All right, Luca, please take it away.
Thank you, Muldrow. And first of all, let me thank the organizers for giving me the opportunity to speak at this series of seminars. Today, I wanted to talk to you about this paper titled The Moduli Space Curvature and the Weak Gravity Conjecture with Alberto Castellano, Fernando Marchesano, and Lorenzo Paoloni. But I would also mention some of the results that we discussed in these other two papers that you see here. So this is the outline of my talk. I will start with a brief general introduction. Then I will tell you why we should be interested in the moduli space curvature. And then I will get to the main part of the talk, which is basically the content of the paper, which deals with the relation between the curvature divergences, rigid limits, and the charge to mass ratios of BPS particles. And then I will sum up and conclude. So the general context of this work is the Swampland program. As you will probably know, the Swampland program tries to identify the constraints that an effective field theory must satisfy in order to be consistently coupled to quantum gravity. And one of the objects of study of the Swampland program are quantum gravity moduli spaces. So we want to understand general properties of these moduli spaces. And so one quantity that one could study is the moduli space curvature. Now you could ask, why should I be interested in that object? I will answer to this question in a minute or so, but before that, let me introduce a couple of Swampland conjectures that will be relevant in the following. First, the Swampland distance conjecture, which states that along any infinite geodesic distance limit in moduli space of a consistent quantum gravity theory, there's always an infinite tower of states whose mass decreases exponentially with the distance, with the field distance. And then there's a refinement of this conjecture that is called emergent string conjecture, which basically classifies these this tower of states predicted by the distance conjecture into two types. It can be either a tower of Kaluza-Klein modes, which signal a decompactification limit where a compact dimension is becoming large, or these states can be oscillations of a critical string that is becoming tensionless in the limit, and then the limit is an emergent string limit. However, in the literature, there are other classifications of infinite distance limits with more subtypes, let's say. So one could wonder what extra physics what extra physics is there associated to these infinite distance limits, and yeah, what else can we say? And as I will try to convince you, the moduli space curvature captures some of this extra physics. So why moduli space curvature? In this paper from last year, we studied moduli space curvature, and we found a relation between curvature divergences and rigid field theory sectors. In particular, we proposed this curvature criterion that states that a divergence in the scalar curvature of the moduli space signals a rigid field theory sector that stays dynamical while gravity is decoupled. So the picture one should have in mind is the following: as we go along the limit, there's the Swampland distance conjecture tower whose mass comes down, measured in Planck units. But if we stay below this cutoff m star, one can still describe these rigid field theory sectors as a 4D effective field theory with cutoff m given by m star. And we studied this in the context of type 2A string theory compactified on Calabi threefolds, and we focused on the vector multiplet sectors and the large volume regime. And we found that whenever there's a divergence in the curvature, this can be written in this way. So there's a finite factor that is the moduli space curvature of this rigid field theory sector. And then there's this ratio of scales, which is basically a change of units, since in the local theory, we measured the fields in Planck units, while in the rigid theory, we measure the fields in terms of the new cutoff, which is m star. And so this quotient of scales is just a change of units, and that's what originates the divergence, since this quotient blows up in the infinite distance limits. However, this is not the end of the story, because these rigid sectors, we observed they come with some extra massive states that are charged under these rigid sectors. And this is what we studied more in detail in this follow-up paper. And we found that these 4D field theory sectors can be seen as the dimensional reduction of higher dimensional rigid theories that we call UV rigid theories. And these charged states under the rigid sector also come in towers with arbitrary charges under the rigid sector. And if we denote by lambda ch the scale at which we start seeing this tower, we found a relation between the degree of divergence of the curvature of the moduli space and this mass scale, lambda ch, and the type of higher dimensional rigid theory, which can be of one of these three types: 5-dimensional superconformal field theory, 6D CFT, or a little string theory. Now, to make a bit more clear maybe what I'm trying to say, let me show you a simple example. So consider, for instance, type 2A compactified on this geometry, an smooth elliptic fibration over a base P2, and take the limit of large fiber. In this limit, we recover a rigid theory, which contains a U1 field, this A1 here, which comes from expanding the Ramond-Ramond 3 form on a basis of harmonic 2 forms, and in particular along the 2 form that is Poincaré dual to the base P2. And this limit corresponds to a decompactification limit to M theory on the same Calabi-Yau. And if we uplift this trajectory to M theory, basically the point in M theory moduli space where we land is corresponds to shrinking the base P2 to 0 size. And then when one takes this limit in M theory, this was studied by Witten, an M5 brane wrapping the base P2 gives rise to a non-critical tensionless string in the limit. And also M2 branes wrapping curves inside the P2 give rise to massless particles. And all of these states, which are the states charged under the rigid U1, are what leads us to a 5-dimensional superconformal field theory, strongly coupled superconformal field theory. So yeah, this was just a simple example. You can find all the details about this and the other two types of the other two cases in the paper that I mentioned at the beginning. So now let me go to the main part of the discussion, which deals with the relation between these three objects. So curvature divergences, rigid limits, and the charge to mass ratios of VPS particles. The setup that we consider is this time type 2B, compactified on Calabi threefolds, and again, vector multiplet moduli space. So this is the 4D action. We have the Einstein-Hilbert term. Then we have the scalar fields that describe the complex structure deformations of the Calabi. And this can be encoded in the period vector that is given by the integrals of the holomorphic 3 form on a basis of 3 cycles. And we work under the assumption that there is a holomorphic prepotential f of x, such that its derivative with respect to these periods xi's gives the second part of the period vector fi, where the capital index runs over 0 and small I. And then we have the gauge kinetic term and the topological term for the gauge fields. And one last thing about this action, the moduli space metric, Gij, is a special Kähler metric. So it's the second derivative of some Kähler potential. And this is its explicit form. Now, it's not very important the exact form of this metric is not very important. You need to focus on this piece here, which is the imaginary part of the second derivative of the prepotential. And why should you focus on that? Because there's a wide literature about how to take gravity decoupling limits in n equals to supergravity theories, and to recover an n equals to rigid theory. And in these constructions, I just cited some references here, but there are many more. In these constructions, from the local prepotential, the prepotential of the local theory, one recovers one inherits somehow the prepotential for the rigid theory, restricting to a subsector of the fields. And the metric of the rigid moduli space reads takes this expression, which reminds of this piece that I was mentioning before. So we take as a definition for a rigid limit this condition where the first piece of the metric is much smaller than the second one, and then basically the metric reduces to the rigid one. Okay, so this is what we mean by rigid limit. But let's see what is the physical meaning of this limit, of this condition. Sorry. It turns out that this condition has a meaning in terms of charge to mass ratios of BPS particles. So BPS particles in this setup are given by D3 branes wrapping 3 cycles in the internal manifold. And such a BPS state is identified by some integer numbers, which are the quantized magnetic and electric charges. And one should also take into account the Witten effect, which is switched on by the topological term in the action, which is multiplied by this matrix R. And this Q tilde is the combination of charges that enter the physical charge, which takes this form, where I is the gauge kinetic function. And then one can also introduce the rigid version of the physical charge for a rigid theory. And this corresponds just to substituting the gauge kinetic matrix I with the imaginary part of the second derivative of the prepotential. And this rigid version is always bounded from above by the local physical charge. This is the intuitive reason is that when going to the rigid theory, one always decouples some U1s. For instance, the graviphoton is always decoupled, and possibly also other U1s. And then the mass for these states can be computed. The mass in Planck units can be computed as the modulus of the central charge, which is just a combination of periods. So with the mass and the physical charge, we can finally define the charge to mass ratio for these states, and which is just the charge divided by the mass in Planck units. And this is due to this inequality. The charge to mass ratio is bounded by this rigid version as well. Now, everything on this slide holds for a generic, it would be BPS particle. But now we pick a special combination of charges that has such that the Q tilde vector has this form. So we have some magnetic charges P mu in the sector that satisfies the rigid limit condition. So this condition that I showed you before. So we just take some magnetic charges in this sector, and then we set everything else, all the other charges, to 0. And for these states, the rigid physical charge and the mass take these expressions. So now, if we compare this with the rigid limit condition, we see that by contracting this expression with the charges P mu, we see that the condition is telling us that the mass of the state is much smaller than its physical charge multiplied by the Planck mass. And so its charge to mass ratio is much larger than 1. And then we showed that in a rigid limit defined in this way, there exists a would-be BPS particle whose charge to mass ratio diverges. I will comment more on this would be at the end of the talk. Okay. We also argue for the opposite implication, namely that if we have some gamma, some charge to mass ratio that diverges, then we are indeed in a rigid limit. And to convince yourselves, you can look at the no force condition for mutually BPS particles, which can be written in this form. Here, this is the contribution of gauge interactions. Then we have the contribution of gravity here, and these are the scalar interactions. And as you see, if gamma is divergent, then the divergence must come from the piece corresponding to scalar interactions, and then the contribution of gravity is totally negligible, and then indeed we are indeed in a rigid limit. So up to now, we saw the rigid limits are in one-to-one correspondence with some charge to mass ratio of BPS particles diverging. And now let's see how this relates to the moduli space curvature. But before that, let me make a couple of comments. So first of all, we focus on weak coupling limits. So in particular, we consider these divergences where the mass of the state is going to 0 and the physical charge is at most of order 1 or order 1 or goes to 0 but at a slower rate. So we leave strong coupling limits out of our discussion where the charge is taken to very large values. And these weak coupling limits can be either of finite distance or infinite distance. They are both included in our discussion. And so for a generic focus, let's focus for a moment on an infinite distance limit. For generic states, these gammas will be of order 1. Because the mass is going to 0, but also the gauge coupling is going to 0. In infinite distance limits, we always have some gauge coupling that also go to 0. So in order to recover these divergences, there must be some hierarchy of gauge couplings. So some of them that goes to 0 faster and some of them that stay constant or that go with a slower rate. And since we are in an n=2 supersymmetric setup, a hierarchy of gauge couplings also implies a hierarchies in the components of the moduli space metric because it's related to the gauge kinetic function. And so this will be important in the following. So now let's get to the moduli space curvature. This is the expression for the curvature, and we have this negative constant piece here and this positive definite piece, which is the one that the source of the divergences. And so if there is a divergence in this expression, it comes precisely from these the sectors of the moduli space the inverse moduli space metric here that are enhanced, let's say, with respect to the average components, and these correspond precisely to the stronger gauge couplings that I was talking about earlier, and we have seen that the divergence can again be written in this form, as I showed you before in the type 2a case. And where we have again this the curvature of the moduli space of the rigid theory, which has this expression where we restrict to these indices in the rigid sector that satisfies the rigid limit condition, and then these factors of scale. But now there are two possible cases in these generic weak coupling limits. If we are in an infinite distance limits, then as before, the rigid moduli space curvature is finite, and what sources the divergence is the ratio of scales, because of the infinite distance. While in the finite distance limits, for instance, in conifold singularities, this ratio is finite, but what diverges is the rigid moduli space curvature. And there can also be actually mixed limits where mixed in the sense that they are like a superposition of infinite and finite distance, and where these two things blow up at the same time. But these are like the two, let's say, basic cases. And we also notice a couple of interesting relations, and namely the divergence of the curvature is always bounded from above by the maximum of these gammas, these divergent charge to mass ratios. And also the divergence scales like the ratio of these two energy scales, which are defined in this way. So lambda weak gravity is the magnetic weak gravity conjecture scale for the rigid sector. So it's just the gauge coupling of the rigid sector times the Planck mass. So this is a gravitational cutoff for our rigid theory for this rigid gauge sector. While the second scale is a purely field theoretical cutoff, and it's basically an estimate of the monopole mass for a gauge theory, and it's given by the gauge coupling to the -2 times the actual cutoff of the theory. This is lambda RFT is the scale at which we actually start seeing new states that are not in our theory. So it's the actual cutoff. And this is very nice because we can see the divergence in the curvature as the parametric decoupling of these two cutoffs, the gravitational one and the field theoretical one, which is, I think, a nice interpretation. So to sum up, we argued that for generic weak coupling limits, the existence of some would-be BPS particle with a divergent charge to mass ratio is in one-to-one correspondence with rigid limits. And also in the curvature criterion, we argued that curvature divergence implies that we are in a rigid theory. And then putting these things together, we would imply that a curvature divergence implies the presence of some would-be BPS state with a divergent charge to mass ratio. And we noticed these interesting relations for these divergences. And now let me conclude with some final comments. So I said would be BPS states because we compute the charge to mass ratios purely from EFT data. Whether these states are actually populated or not is a UV question. So and in general, we find that some of these states are populated, but not all of them. And also these states are typically not extremal. So if they were extremal, then the charge to mass ratio would be equal to the black hole extremality bound, but in the corresponding charge direction. But we in general, these are not extremal. So we wonder whether there's any relation between the curvature, moduli space curvature, and the black hole extremality bound. And also, as I mentioned, we discussed the weak coupling limits. We left out of the discussion strong coupling points. So it would be interesting to attack also these other kind of limits. And everything we said was about n equals 2 vector multiplet sectors. So another interesting venue would be to explore these things in hypermultiplet sectors and minimally supersymmetric setup. With this, I conclude, and I thank you very much for your attention.
All right, let's thank Luca for the very interesting talk. Do we have questions from the audience? Nacho, please go ahead.
Hi, Luca. Thanks for the talk. You mentioned, like on the last part of the presentation, that you find those relations that you have always,
Yes.
like, yeah, that one there, that the diverging curvature always does so like less fast than like the faster divergent scalar to mass ratio vector. Do you have like any explanation for that? Or is just like an observation that you
Not really. It's an observation that we saw in all the limits that we analyzed. We looked at large volume limits, conifold limits, Seiberg-Witten limits, and yeah, it's an observation. We don't really have a deep reason why it should be so.
Do you have like
At-
any bound on how fast, at least just from observation, how fast those scalar charge ratio vectors can charge mass ratio vectors, sorry, can diverge? Like, do they diverge like exponentially fast, or like how do you have anything on that?
You mean exponentially in the distance?
In the distance, yeah. Or is it like?
I think it's yeah, I would say it's exponentially fast. Yes.
But just from observations, you don't
Yes.
have like any further.
Yeah,
Okay,
yeah, yeah.
thanks.
Yeah, no, it's yeah, observations. Yeah.
Thanks.
Sure.
Any other questions for Luca? Well, we can chat also after in a moment where it will no longer be recorded. Perhaps people will have more questions then. So let's thank Nikolaus and Luca again for their very nice talks. Great. Adriana, is there anything we should say that we haven't said?
This was the last seminar of this year, and I guess we'll see you next year. Thanks a lot, everyone, for joining today.
Thank you.